Ladies and gentlemen, welcome to plenary session number 2, Remote Superspectral and Hyperspectral Sensing from Space. I'm honored to be a moderator for this session on behalf of Israel Space Agency. My name is Eyal Ben Dor. I am a professor at Tel Aviv University and the head of the Remote Sensing Laboratory in the Department of Geography and Human Environment there. This session is divided into two parts. Superspectral activity at the national level, focusing on Venus project, and the hyperspectral activity at both national and international levels. Superspectral defines sensors that have 10 to 20 broadbands, whereas hyperspectral refers to sensors with more than 30 narrowbands. The first three speakers will talk about Venus, a French-Israeli mission to put a superspectral sensor into orbit. And the last three speakers will cover 3 different international programs to put hyperspectral sensor into orbit. We will move directly to the first part. And the first speaker for the Venus mission will be Mr. Ehud Hayun, from the Israel Aerospace Industry Mabat. His talk will be on Venus System Engineering Overview.
Thank you very much.
Mr. Hayun has been working in Israel Aerospace Industry Mabat Space Division since 2005. He is the Chief System Engineer for the Venus program and the head of LEO satellite operations at Mabat Space. He has MSc and BSc from the Technion, Israel. Mr. Hayun, the floor is yours.
Good evening. So the Venus mission is a cooperation between the French Space Agency, CNES, and the Israeli Space Agency, EISA, in cooperation with Rafael, Elbit Electro-Optic Systems, and IAI MBT Space Division as its prime contractor. The satellite has 2 payloads for its 2 missions. The VSCC, a superspectral camera with 12 bands for the scientific mission, and the IHAT, Israeli Hall Effect Thruster, for the technological mission. The Venus mission is composed of 3 main phases. The first phase is called VM1. You can see it in green right here. This is the scientific mission phase. During VM1, the satellite will acquire images of about 110 sites across the world. It is required to repeat the sites and revisit them every 2 days and perform the imaging in the exact same conditions. Therefore, it will be set into a sun-synchronized orbit with a repeating ground track. It's a very unique orbit. After 2.5 years, it will complete its scientific mission and begin the second phase, VM2. VM2 is a technological mission, an orbit descent from 720 kilometers to 410 kilometers using its Hall effect thrusters. We estimate this phase will take about 6 months. And at the end of this phase, the spacecraft again will enter a sun-synchronized orbit with a repeating ground track and begin the third mission, VM3, which is the most challenging one on a technical level because the satellite will have to resume its scientific mission, acquire images, while the IHAT system, the Hall effect thrusters, will perform small orbit corrections in order to overcome the intense drag effects that are present in such low heights. The total mission duration is 4 years and 3 months. The system is composed of 5 mission control centers spread in different places of the world. We have a GCS, a ground control station in Israel, in Ehud, Israel, responsible for the housekeeping of the spacecraft. We have a ground receiving station, VRS, acronymed VRS in Kiruna, Sweden. We have a scientific mission center located in Toulouse, France, for dealing with all mission planning aspects and image processing. We also have a scientific mission center in the Negev Desert in Israel, dealing only with the Israeli sites. And finally, last but not least, we have the Technological Mission Center, the TMC, responsible for the planning and execution of the technological tests, the IHAT tests. Sorry for that. The satellite is based on our generic bus platform, acronymed IMPS. This platform is also used by Texar and OPSAT 3000 satellites. It's a very capable platform, and we are happy for that. The total weight is 265 kilograms. It has a very accurate attitude control system with star trackers and 4 reaction wheels. Also with a set of core sensors for emergency cases. And we have on board the hydrogen propulsion system, fully capable of supporting the orbital requirements in VM1 and also for emergency cases. It's also available. All the systems have built-in redundancy mechanisms and are doubled. We have, it's like NOAC arcs. We have 2 of everything, just to be sure and to be safe. On your left, you can see the ion thrusters. I will let Jacob talk about them later on. And on the right side, you can see the camera. It's, of course, located on the center of the bus. And now I will move to the mission aspects. And I will talk about the scientific mission and later on the technological mission. So, the scientific mission is all about acquiring images around the world in a repeating manner. So that means that the satellite has to acquire the images at the exact viewing angle and at the exact time of date. And we're doing that by positioning the spacecraft in a unique orbit. It's a sun-synchronized orbit with a repeating ground track, also known as a phased orbit, throughout the mission. And this unique orbit enables the satellite to go over and over the same ground tracks throughout the entire mission, throughout the entire 2.5-year period. And therefore, easily produce later on multi-temporal analysis of the scientific areas. So you can see on the lower right side an example of a multi-temporal analysis performed that could be performed by using the Venus images. This example was prepared, by the way, by the CNES image processing team located in Toulouse, and they have many more examples at the CNES website. You can see this example is about monitoring a water reservoir and measuring the ice surfacing over this reservoir. And as I said, the scientific mission is covering 110 sites every 2 days. You can see here an example of revolution number 17. Revolution number 17 out of 29 revolution. This revolution only covers 18 sites. It goes over Western Europe and West Africa. It's quite a crowded revolution, and we are constantly making an effort to increase the capacity of the system, bring in more sites into the scientific mission, and we are doing that by means of improving our mission planning softwares, even the satellite software, and it's a big effort, but it pays off, because originally the scientific mission, when Venus was initiated, was required covering 50 images per 2 days, and we easily were able to increase that number to 70. And later on, when the demand rose, we increased that capacity to 110 sites every 2 days, and we are now working on the next level of improving this capacity to 160 sites. It's not agreed yet, thank you, but we are approaching this, and of course it's very important for the scientific impact. Moving on to the technological, okay, I will just say shortly, the camera was specifically designed and manufactured for the Venus program. designed and specified by CNES and manufactured by ELOP. You can see on your left side the camera at the ELOP premises. Down here you can see the satellite before and after camera integration. On the right side you can see a cross-section of the camera. Essentially, this camera houses 12 detectors, and therefore every image product contains 12 images. It's 12 cameras packed into one. It's really a masterpiece. It deserves a lecture of itself. Move on to the technological mission swiftly. So, the technological mission is all about changing the orbit. It's really active throughout the mission. During VM1, we intend to operate the IA thruster in order to verify the system's capabilities. But the real challenge, of course, is VM2, which is essentially one continuous orbit correction, orbit maneuver. The orbit is changing constantly. The systems are working very hard in terms of power consumption, heat dissipation, etc. And then when the satellite reaches VM3, every now and then, it will have to perform autonomously an orbit correction in order to keep the orbit in the right track. The entire procedure is performed fully autonomously by the satellite. It decides when to operate the engines and how to point the thrusters to the desired direction. It also has full autonomy over the decision of which engine should it operate. You can see that now it switches from engine 1 to engine number 2. And Rafael and the IAI engineers invested a lot of wisdom into this system. Now let's see engine number 2. Okay. So up until now, I told you about one satellite housing 2 new payloads with 3 mission phases and 3 different orbits and controlled by 5 ground stations. This should work perfectly, right? So the answer, of course, is that things do tend to fail in space. Space is hard, and this is why we invest a lot of energy into testing and qualification of the system. We have 4 layers of qualification phases that hopefully will reveal all the holes in the cheese. The first layer is the spacecraft integration. Of course, second layer is the verification and validation campaign, where we focus on non-nominal cases and try to trigger all the fallbacks of the system, all the redundancies. Third layer is the system test campaign, where we involve all the ground segments, first in pairs, and then later we involve MBT, CNES, Kiruna. Everyone are involved and Rafael, of course, in nominal operations of the spacecraft on ground, of course. And lastly, we will have the integrated functional test, where we use the real satellite and the real ground stations and simulate a day-in-a-lifetime scenario that should resemble the reality. Finally, and this is my last slide, we are all dictated, even my lecture, by time and schedule, and even the Venus project has a schedule. It has a very long history, but with your permission, I will skip to the present. We are currently here, running, on the system point of view, we are running a very long and intense testing and qualification campaign, where all parties are involved and invested in. On the hardware level, the spacecraft is currently going its final integration phases. We believe the integration will be completed by the end of this year, and then it will enter a series of environmental tests, vibration, shock test, thermal vacuum, etc. The entire test campaign should be completed by August 2016, and then we'll be ready for launch. We have a secure launch with Vega launcher by Ariane Space, together with another Israeli satellite, OPSAT 3000, The launch will be during the year 2017. I will hope that a launch window will be declared early next year. That's it. If you have any more questions, I will be at the IAA booth throughout the conference, so please come see me. Thank you.
Thank you very much. Thank you, Mr. Hayun, and we run to the second speaker. I would like to ask the speakers to keep 10 minutes sharp, please. The second speaker of this Venus session will be Professor Arnon Karnieli from the Remote Sensing Laboratory of the Blaubstein Institute of Ben Gurion University of the Negev. He will talk on Venus, the scientific mission. Professor Karnieli is the Israeli principal investigator for the Venus mission. His main research focuses on processing spaceborne, airborne, and ground spectroscopic data of dry land and with respect to desertification and climate change processes. Professor Karnieli has published more than 160 papers in peer-reviewed journals and is ranked in top of the most cited researchers in remote sensing worldwide. Besides Israel, he conducts worldwide activities in Central Asia, Mongolia, China, and West Africa. Professor Karnieli, floor is yours.
Thank you very much, Eyal. I'll talk about the Venus, the scientific mission of this spacecraft. This slide you saw before, as you saw in the previous presentation, Venus has 12 spectral bands from the deep blue through the visible, near-infrared, and the red edge regions. And the range covers a lot of spectral features of vegetation, soil, water, and other features. In this regard, the scientific application of the Venus mission follows three routes. The first is the land, and specifically vegetation application for particularly agriculture and precision farming, because we have a very high revisit time and spatial resolution. With regard to the land, we can create also a digital elevation model. Talking about water, we aimed at monitoring water quality in inland and coastal water. With respect to the atmosphere, we will detect aerosol optical thickness, water vapor, and also cloud height. Monitoring the state and condition of the vegetation is the main application on the main goal of the scientific mission. We can implement this at the vegetation state by vegetation indices, and they commonly use a normalized different vegetation index is based on two spectral bands, the near-infrared and the red. However, we have more spectral bands in order to implement also more advanced vegetation indices like EVI, the enhanced vegetation index, that overcome the limitation of the DVI in terms of atmospheric absorption, in terms of high biomass, and so on. The location of the bands was carefully selected between the atmospheric absorption features, particularly the four bands that are located along the red edge. The red edge is the dramatic increase of the reflectance of the vegetation from the red to the near-infrared. And this is supposed to provide more accurate information about the physiological features like chlorophyll, nitrogen, leaf area index, and several more. With respect to soil, we can use the visible bands to create several soil indices like the grass index that rely on the red and the blue spectral regions, or hematite index that relies on the blue, green, and red spectral bands for assessing the iron oxide in the soil. Three water elements can be detected in the visible region. These are chlorophyll, which indicate pollution in the water, sediments that indicate land erosion, and dissolved organic carbon. We can assess these elements by combination of different spectral bands. Moving to the atmosphere, we can use the 550 nanometer band in order to detect the aerosol optical thickness. That is indicator for dust, biomass burning, volcanic ash, anthropogenic air pollution, and so on. We can use the two bands in the near infrared to assess water vapor in the atmosphere for atmospheric correction. We have two similar red bands that are located in different detectors, but looking at the same point on the ground with angle of 1.45 degrees apart. From this small stereoscopic effect, it will be possible to generate DEM and also to classify clouds by their heights. The main advantage of the Venus is the very high revisit time of 2 days. This can be used for different applications. For instance, to classify the land cover, time series of images increase the classification accuracy. We can also assess different phenological features and their consequences. The high revisit time can use also for monitoring fast response to environmental disasters such as pollution, dispersion in the sea, as you can see in these slides. And also multi-temporal cloud detection and able image restoration. We will use 4 different levels of products. Level 0 will indicate the single date and single angle acquisition. This will be the basic archive product in 5.3 meter resolution. Level 1 is the single date and single angle acquisition, but top of the atmosphere, that means without atmospheric correction, but with a geometrical correction at 10 meters. Level 2, it's the same product, but by surface reflectance, that means after atmospheric correction. And level 3, it's a 10 days composite of a single date and single angle acquisition, but also different products like NDVI, LAI, chlorophyll, FAPAR, and so on. These are several examples of the end product, like NDVI, LAI, photosynthetic vegetation cover, FAPAR. In summary, I would like to say that there are different space missions which has a better spatial resolution, better spectral resolution, better temporal resolution. But none of these systems that currently in space has the composition of these 3. And this is the uniqueness of the Venus mission. The high spatial resolution is used for monitoring individual fields and provide information for precision farming. Several bands, including along the red edge, is used for assessing the state of the vegetation. Several bands for assessing water quality. high revisit time to acquire rapid changes of vegetation and water quality, as well as cloud mask, and the duplication of the red bands will be enable us to produce the EM and cloud heights. Thank you very much for your attention.
Thank you, Professor Karnieli, and we move on to the third speaker for the Venus session. This will be Mr. Jacob Hershkovich from Rafael. The title of his talk will be Venus, the Technological Mission Using Electrical Propulsion. Mr. Hershkovich has been working at Rafael, Israel, for more than 30 years in various positions. He currently serves as the Chief System Engineer for the Space System Directorate. He is also the manager of Venus project for Rafael and oversees the R&D activities for the Space Directorate. Mr. Hershkovich received his MSc degree in the System Engineering from the Technion in 2000. Mr. Hershkovich, the floor is yours.
Thank you. The second mission of the Venus satellite is the technological mission. This mission uses a newly developed electric propulsion system as the payload, as a secondary payload. The main goals of the technological mission is to verify and validate the Israeli Hall effect thruster in space. It will demonstrate the orbit maintenance of imaging, during imaging. It will transfer the satellite between two-layer orbit, and at last it will enable the precise imaging mission in a high-drag environment. The electrical propulsion system employs two Hall effect thrusters, as you see here, a PPU, a power processing unit, a fuel tank, a lot of valves, a lot of hardware, pipes, harness, and so on. You can see in the display area the model of the propulsion system of Venus satellite. The electric propulsion system, Hall effect thruster, is using xenon as its propellant. We have a anode and a cathode. The cathode emits electrons. The electrons are accelerated in the magnetic field, and they collide with xenon atoms that are exiting from the anode. Then for each collision, a xenon atom becomes an ion, and since it is positively charged, it is emitted and accelerated outside the thruster, outside the channel, at a very high velocity, and this is what gives the thrust to the satellite. We have, like Ehud said, three phases of the mission. In the first phase, Venus Mission 1, the main challenge is to enable the imaging from 720 kilometers, and we will control the orbit once a month. In addition, once a month, we will perform an experiment. During this experiment, we will have a series of pulses of the thruster and then download the data of the orbit. With this data of the orbit, we will be able to estimate on the Technological Mission Center what was the performance of each thruster. Of course, the other goal, other than that, is to validate and prepare and make it ready for the other two phases, VM1 and VM2 and VM3. For the VM2 mission phase, we will transfer the satellite from 720 kilometers to 410 kilometers. In addition, we will change the inclination for 1.2 degrees, and this is because we need to keep the orbit sun-synchronous and Earth repeating. The duration of the transfer will be about 6 months or more, and we have a high challenge of maintaining the high delta V of 350 meters per second and very accurate insertion into the VM3 orbit. The last phase, the VM3, will last about 1 year, and here we will continue the imaging, the precise imaging, but here, since we have a high drag environment, we will have to control the orbit every 4th revolution. So the other 3 revolutions will be devoted to imaging, and we will cope with as many as we can imaging targets. So in total, we will be able to image for 3/4 of all the revolutions. We have a lot of operating profile constraints in the technological mission. We have to operate the thruster only in the illuminated part of the orbit because it needs power, and we will have to comply with a lot of constraints to avoid blinding of the sensor from the sun, the camera from the sun, the camera from the velocity direction. We will have to cope with the spacecraft power and the agility of the spacecraft, and these are a lot of limitations and constraints, and for this we needed to develop an autonomous orbit control. But first of all, the traditional orbit control is working like this. The satellite is getting data from the GPS, and it downloads this data to the ground control. The ground control estimates the orbit, and it also estimates what are the control pulses that are needed for the thruster to control the orbit. It uploads to the satellite these commands, and the satellite is performing this thruster firing at the designed time and place. For the autonomous control, we avoid and take to the minimum all this operation, and the ground control is uploading to the satellite the orbital parameters. The satellite is getting the position from the GPS satellite, and it computes autonomously on board what are the control sequence and firing of the thruster, and it performs autonomously at the right time, at the right place, these control pulses. In order to perform this autonomous control of the orbit, we developed what we call technological mission module. Acronym is TMM, and this is a software module that is in charge of the technological mission and is a piece of software embedded in the software of the satellite. Among its function is to perform the experiment with the I-hat, to control the orbit, to control the ground track, to monitor the payload, the electric propulsion system, to get telemetry, and much more. And at last, we have the last link is the Technological Mission Center. This is a ground facility that is getting all the data acquired by the satellite, and it computes all the performance of the thruster and of the orbit. It prepares a report, and we will distribute reports. You can see here a few windows of this Technological Mission Center. You can see the I-hat data processing and modeling of each thruster, and you can see here the simulation and the estimation, what will be the performance of the orbit. And in the end of this mission, we will have a precise model of the newly developed thruster and a precise model of the orbit control performed by the satellite. Thank you.
Thank you, Mr. Eshkovitz, for being on time. One thing now to do is to go to the second half of our session. Okay, now we will move to the second part of this session dedicated to hyperspectral activity from space. First, I would like to draw your attention to the new initiative between Israeli and Italian Space Agency to construct an innovative hyperspectral mission from space, the Shalom program. Aside from being just another hyperspectral remote sensing mission, the Shalom program is driven by operational and commercial needs, consists of highly unique characteristics. It will have 241 narrow bands across the visible, near-infrared, and shortwave infrared spectrum with a nominal 10 meter pixel size and PAN channels of 2.5 meter, as well as high temporal resolution of 2 days over land and coastline areas. With several other hyperspectral missions being carried out by different space agencies and organizations, knowledge and sharing the information exchange between groups has become highly important. To that end, a technical committee of International Satellite Imaging Spectroscopy, TC-ISIS, has been established in 2007. The strategic goal of the TC-ISIS is to apply the technology from primary R&D activity today toward operational data acquisition, standard product and protocol, and efficient delivery by 2016. The group was founded by Dr. Alex Guest from Xero, Australia, and Dr. Carl Stenz, University of Leidenburg, Canada. The initial number of members was 17, but now stands at 140, consisting of all relevant players in this technology. The chairman person for the TC-ISIS today is Mr. Andreas Mueller from the DLR, who is the first speaker in the second part of this mission. I therefore call Mr. Mueller to present his talk entitled An Update on the Status of German Imaging Spectrometer Mission EnMAP, which today seems to be the next available hyperspectral sensor from orbit. Mr. Mueller is the head of the Land Surface Department at DLR, German Remote Sensing Data Center. He received his diploma from the University of Munich in Geology and Remote Sensing in May 1990. Mr. Mueller has 25 years of experience in processing and evaluation of airborne and spaceborne imaging spectrometers and multispectral data. He has led many campaigns in Germany, amongst other European countries, Israel and India. Mr. Mueller is currently a co-investigator on the German hyperspectral satellite mission EnMAP and a member of the EnMAP Scientific Advisory Board. Since 1996, he served as the chairman person for the Imaging Spectroscopy Special Interest Group of the European Association of Remote Sensing Laboratory. Mr. Mueller, please.
Thank you very much for this kind introduction, Eyal. I have the pleasure to introduce you to our German hyperspectral mission today. And when I was entering El Al, the boarding procedure of El Al in Munich, the security officer asked me, "Why are you giving this presentation?" And it's a good question because actually Luis Ganter is now leading the scientific evaluation of EnMAP, which was, Charlie Kaufman was doing that for years before. And probably the correct answer for that question of this security officer is, I'm probably one of the few persons that is accompanying EnMAP from the proposal phase up to now. And you see that there are many, many people involved in this mission, and I will show you how the program is structured and where we are standing right now. As I said, the scientific principal investigator is seated at the GFZ, the Geo Research Center in Potsdam. Project management is done by DLR, so this is a purely German mission we are talking about. And also large components, or the majority of the hardware components are manufactured in Germany by OHB, a German company, which is true for the sensor part and the instrument part of things, as well as the platform, the satellite platform that we are talking about. The ground segment is prepared by DLR again, and this is also where I have been involved in the mission as ground segment manager for a couple of years. So operations, payload, and the data processing is done at DLR. In EnMAP, we talk about a scientific mission, but an operational scientific mission, so a lot of emphasis is put on the system performance and the instrument performance of the spectrometers, and also on the pre-processing, calibration, and validation of the data that we are producing. The good news about EnMAP is that numbers, requirements have not changed, and that's a very good thing, and we are very proud of. We are able to keep the requirements that originally were developed and stated by the science community. We keep those requirements, and we have technological progress that make us believe that we can fulfill the requirements. We had to compromise, and the number that has been changing most over the years was actually the launch date. So we're now very happy that the launch date has not been moving around for almost 2 years now, and we talk now a launch date of mid-2018. If we look a little bit closer at the main mission parameters of EnMAP, you see that we are talking about a push broom instrument on a sun-synchronous orbit with 11 hours local descending node equator crossing time. The spectral range is from 400 to 1,000 nanometers in the first spectrometer, in the CNR spectrometer, and from 900 nanometers to 2,450 nanometers in what we call the shortwave infrared section of the electromagnetic spectrum. The spectral sampling distance, the spectral resolution, if you want, is quite narrow. In the visible near infrared, we are about 6.5 nanometers, and in the shortwave infrared, about 10 nanometers. Why is this about? We are using prisms as dispersive elements, and as you are aware, it is very difficult to realize a constant spectral sampling interval with prisms, so we have a slightly varying interval here. Data acquisition will be limited, so we are not a mapping mission. We will only be able to record strip lengths of 1,000 kilometers in one orbit and a total of 5,000 kilometers per day in 19 orbits at a swath width of 30 kilometers. So you will see that mapping an entire continent is somewhat of a challenge. We will not be able to do that very quickly, but we will be able, with an agile satellite that can be turned and directed 20, plus minus 20, 30 degrees off nadir, to revisit a given ground target within 4 days, and on quasi-nadir observation conditions, we revisit every point on the Earth in 27 days. Mission design is for, lifetime is for 5 years, so we can use the instrument for 5 years to monitor land surface processes. The instrument design, and I'm not an optical engineer, and I'm not going into very much detail here, is based on a telescope, on a 3-mirror anastigmatic optics. We have a field stop assembly that is realized as a field splitter, so with in-field separation between the two spectrometers. One being the visible near-infrared spectrometer that is that you can see in the upper part of this slide, and the shortwave infrared spectrometer on the lower side of this image here. The challenge here is that we are recording the same part of the Earth's surface with a time difference of a couple of milliseconds, so we're not looking at the same spot on the ground simultaneously, which gives us some challenge later on in the data correction. I have been talking about a high-performance, stable operational mission with high quality. One means of ensuring the quality of a spectrometer is to control it on orbit and use on-orbit calibration facilities to monitor stability, detect drifts, and be able to adjust for it. So we have a quite complex and challenging calibration setup on board the instrument. I'm not going in detail on this one. Just let you know that we can control the spectral behavior and the radiometric behavior of the system on orbit, and then should any drifts or any changes in the instrument occur, be able to adjust our processing capabilities and processing chain on the ground. EnMAP, being a science mission, of course, has its own strategic science goal. and a general mission framework that was set up by the EnMAP Science Advisory Group in support of the PI. This document is also available on the internet, so if you would like to have a closer look at it, please feel free to do so. This document hopefully helps us to ensure the exploitation of the mission and also will allow us to check the mission completeness at the end of lifetime. The current focus in science is on agriculture, forests, ecosystems, soils and geology, a point that I will come back later on and show you why we are thinking that this is important, coastal and inland waters as well as urban infrastructures. As we are now in EnMAP for quite a while, we would like to start working with EnMAP data. We have got an EnMAP data simulator that will allow us from existing data sets, be it ground spectral, be it airborne imaging spectrometer data, simulate the performance of EnMAP and do some data evaluation already. So I can now proudly present to you the first EnMAP image that was taken back in 2008. So this is based on an airborne hyperspectral survey in Costa Rica, where we tested the availability or the potential of EnMAP to delineate between photosynthetic active, non-active vegetation and soils. The idea behind that is if you have bare soil, it is prone to erosion to a higher percentage as covered ground. And combining this information with a digital elevation model, in this case also derived from Earth observation, from SAR imagery, we can compute soil erosion risk being one important factor in sustainable agriculture. Usually these type of evaluation is not easy to perform. It takes quite a bit of experience, and also you have to have your software tools in hand. Part of the EnMAP science program is to allow people to use state-of-the-art algorithms freely available and available on the net. So we have tools collected together and assembled them in what we call the EnMAP box, which is freely available for download. And I was surprised to hear that we have over 2,500 downloads so far from this software tool. So I think the people are quite interested in these kind of things as well. One of the tools that is included in here, and I put this again because I think that soil and soil fertility in the long term will be very important variables and information on the long term to assure food security on our planet. We'll give you the tools on hand to, from imaging spectrometer data, compute important soil information like iron content, clay mineral content, and soil organic matter content, and so on, so as you see them. These tools will be freely available to the community everywhere in the world. And this is another, my last slide now, another nice component about the EnMAP mission program. Not only will we have a state-of-the-art instrument in space soon, but we will also have the people that are able to deal with the data that are upcoming, because we are preparing them, and this is the third group of EnMAP young scientists that are trained within the framework of this mission. So we also will have the people knowing how to deal with spectroscopy data. And that's my last slide to show you that EnMAP already is in existence. It's not a microsatellite, it weighs 1 ton once it's set up, and we're really looking forward to the launch in mid-2018. Thank you very much.
Thank you, Mr. Mueller, for this talk. Now we will move to the second speaker of this session. It will be Professor Jose Moreno from the University of Valencia, Spain. He will give a talk on mapping terrestrial vegetation photosynthesis on a global scale with high spectral resolution imaging spectroscopy, the Fluorescence Explorer FLEX mission. Professor Moreno is a professor of Earth physics and head of the Laboratory for Earth Observation of the Image Processing Laboratory Scientific Park at the University of Valencia, Spain. He is working on different projects related to development of new technologies for the satellite Earth observation, advanced data processing method for imaging spectrometer, and the modeling of and monitoring of land surface processes using space observations. Professor Moreno has served on advisory committee for ESA, the European Commission, the European Science Foundation, EU Metaset, NASA, and other international institutions. Among his many activities as the advisor for several space agencies worldwide, he is currently principal investigator for the FLEX ESA mission and a chairman of the FLEX Mission Advisory Group. Professor Moreno, the floor is yours.
Thank you, Eyal. I will introduce the FLEX mission in the context of the ESA Earth Explorer program, which is based on very high spectral resolution imaging spectroscopy. In order to be within the Earth Explorer, you need to address a relevant scientific topic using an innovative technique that has not been used before for Earth observation. And the scientific topic that we will address is the terrestrial carbon cycle in the context of climate change and global warming. We know the future of climate on Earth basically will depend on the balance between how much carbon we are releasing to the atmosphere due to the human activities, how much carbon vegetation is able to take from the atmosphere and assimilate the carbon in vegetation on ground. If you look at the different components of the carbon cycle, the biggest one is actually, the largest flux is the photosynthesis flux, bringing carbon from the atmosphere to the surface. And there is a large uncertainty on the actual value of this flux on interannual basis, but also the spatial distribution of carbon sinks. Actually, is this uncertainty on the terrestrial carbon balance, which creates problems in the simulation of future trends in climate change. And actually, we know that the main problem in predicting what will happen in the climate on Earth came from the coupling between the carbon and water cycles and how vegetation will respond to these environmental factors, particularly taking into account the vegetation stress conditions that drive this relationship between carbon and water cycles in the global climate cycle. But on the other hand, there is an obvious importance of this activity on the societal benefit, because we know that the expected increase in population on Earth will bring also the fact that we will be a pressing need for more and better crop production. And better crop production means optimal photosynthesis to get optimum irrigation and fertilization. And we know photosynthesis is a key component that actually responds to all the environmental factors and different stress conditions. So photosynthesis is tracking all this variability in vegetation stress conditions, and this will have a direct impact in the optimization of food resources for the growing population. The innovative technique that we will use for that is chlorophyll fluorescence. When chlorophyll molecules absorb light, the electrons are moved to these excited energy states, from which, due to internal energy conversions, actually the energy which is used for photochemical processes, some of the light is released from the lower part of the excited energy state as fluorescence. And this loss of energy from the absorption to the emission implies that the fluorescence emission takes place a longer wavelength than the light absorption, and this is what allows us to separate both the absorption of light and the fluorescence emission. This is important because the molecule of chlorophyll, when it's excited to this chlorophyll state, there are basically 4 different mechanisms to the excitation of the molecule. And the 4 different mechanisms are coupled through this physiology of the plants, so that by measuring fluorescence, we can say how much of the light that was absorbed by vegetation is actually used for photosynthesis. And this is the key thing, because not all the light, and not always the same, is used for photosynthesis from the light that is absorbed. In fact, until now, most of the information we are acquiring about the vegetation condition on the surface came from the so-called vegetation spectral signature based on vegetation reflectance. This is the base of imaging spectroscopy until now. But recently, we have also the possibility to have the fluorescence emission spectrum, which is a new spectral signature of vegetation that provides additional information over the information which is already provided by reflectance. The problem is that fluorescence emission takes place in the range between 650 to 800 nanometers, but is a very small fraction as compared to the light which is already reflected by the surface. So basically, if we will measure the actual reflectance of the surface, that will be in this plot, the red curve, which is shown here as true reflectance. Because we have fluorescence emission in this spectral range, we will have an additional contribution, which will be the lower envelope of the blue curve. If there will be no spectral absorptions in the solar irradiance arriving at the surface, we will not be able to decouple the true fluorescence from the apparent fluorescence, the true reflectance from the apparent reflectance that will incorporate the fluorescent signal, because the two curves will be extremely similar. It is just the fact that the solar irradiance arriving at the surface has spectral features, spectral absorptions, either due to solar effects, so basically the solar chromosphere absorptions, or absorptions in the terrestrial atmosphere, like oxygen or water vapor. Every single absorption will be one spike in this spectrum. So by measuring in high spectral resolution, we will resolve these spectral absorption lines, and we will be able to decouple the fluorescence emission from the true reflectance. In fact, if we plot the separability between fluorescence and reflectance as a function of the spectral resolution, you will see here that for very low spectral resolution, the two signals will not be able to be separated, so they are basically confusing. But as soon as you increase the spectral resolution, there is a kind of optimum resolution, which is in the order of 0.3 nanometers, where you get an optimum separation between the fluorescence emission and background reflectance. We need definitely this very high spectral resolution to decouple the different contributions to the signals. If we would individual spectral bands, we will not be able to decouple the different contributors. It is just the fact that every contribution, aerosols in the atmosphere, water vapor, surface pressure, any contaminant in the signal will have a different spectral signature. So by looking at the spectral behavior in the whole spectral range, we can decouple the different contributions. Even more, we need to know how much light has been absorbed by chlorophyll, how much light has been absorbed by vegetation, but not by chlorophyll, but by other chemical constituents which are not playing a role in the photochemical processes. And for that, we also need high spectral resolution in the interval of chlorophyll absorption. Even more, the relationship between fluorescence and photosynthesis depends on the status of the photochemistry of vegetation, basically how vegetation dissipates the heat. And this is reflected as very little changes in the spectral reflectance of vegetation in the interval between 500 and 600 nanometers. So these different curves here indicate different chemistry of the plant, and the different chemistry means different adaptations to heat dissipation. So by putting together all the elements, it's obvious that we need higher spectral resolution spectroscopy to really resolve all these processes. Now, if we will put all these elements together, taking into account that we need to characterize the atmosphere, we need a number of information about the surface, that will imply a really complex and probably very expensive mission. So the way we are planning to implement this mission is by flying in tandem with another mission, which is Sentinel-3 from the Copernicus program. The reason for that is that Sentinel-3 will be for sure available. It will be an operational mission that will be flying at that time. And Sentinel-3 will provide a number of spectral information, which is important for us. We will just fly very near Sentinel-3, with a separation in the order of 10 seconds. And by using the information, the combined information from Sentinel-3 and FLEX, we will be able to get all this information together. The other reason for flying with Sentinel-3 is that the overpass time is 10 o'clock in the morning, which is the optimal overpass time for vegetation fluorescence measurements. Actually, the information provided by the two instruments is very complete. As you see here, the information provided by Sentinel-3 is already very rich. It covers from the visible, from 400 nanometers, up to the thermal infrared, by different sensors, with different observation geometries. So that FLEX will provide just a very high spectral resolution, but only in the spectral range where we really need this information to be combined with information from Sentinel-3, as is indicated here in the table. So this is the kind of spectral resolution that we will be able to see, which, by the way, is a factor 100 over the imaging spectrometers that have been presented before in this session. We have two technical concepts at the moment because we had just finished phase B1. The two technical concepts, the key element is that they are both based on a rather small instrument which is able to fly in a rather small platform, just because we are making use of this tandem flight with Sentinel-3 to save instrument and max in the payload. The launch date at the moment is set for 2022. So at the moment we don't have real data, but we have on the one hand the technology, and we have building breadboarding the instrument, detectors, and a number of things the technology side. But on the scientific side, we have an airborne demonstrator, which is already flying and is able to provide information pretty much similar to the information that we will get from FLEX later on. And on the other hand, we have a quite detailed FLEX end-to-end mission simulator that allow us to test in a very realistic scenario all the conditions of the mission, to simulate the data and to test the retrieval algorithm. So in conclusion, we realized that plant photosynthesis is a key component of the global carbon cycle, and all the information which is available until now, based mostly on vegetation reflectance, is able to provide the potential photosynthesis that plants on Earth are able to do. But fluorescence will provide the actual photosynthesis, which is a major step forward in the constraining models for carbon assimilation. On the other hand, there is a great potential for applications in agricultural growth production, because basically food security and things related to that will basically imply a better estimate of photosynthesis. There is many ongoing activities ongoing now involving a very large community, many new airborne instruments, developing field instruments for ground validation networks, new models, new applications. And FLEX will really exploit the potential of this very, very high spectral resolution imaging spectroscopy that has been developed before in other missions like EnMAP and other missions that have been already presented in this session. Thank you very much.
Thank you, Professor Moreno, for this talk. And now we will run to the third speaker of this session and the last speaker of the entire sessions. This will be Dr. Stefano Pignatti from the National Research Center, CNR from Italy. He will talk on agriculture and land monitoring products developed by the Sub-4 Prisma project in the context of the Prisma mission. Dr. Pignatti has been a researcher at CNR since 1995 and currently works at the Institute of Meteorologists and for Environment Analysis, ENMAP. Since 1990, he has been working on hyperspectral remote sensing from both airborne and satellite platform. He is involved in most of the Italian Space Agency ASI projects to support and develop Italian's hyperspectral capability in space. He is currently the coordinator for the Sub-4 Prisma research project in the framework of next ASI hyperspectral mission to orbit, Prisma. Please.
Thank you. So, as Eyal introduced me, this talk is basically on the research that we've done, just supporting by ASI for the developing environmental products by using Prisma. Since for that, this slide showed that this participated by 3 Italian universities, 2 research groups, and also the military academy of Livorno. The talk is divided basically into parts. The first part is just a very small, short overview of the Prisma mission, and the second part is an overview of the environmental products we have exploited within the Sub-4 Prisma project. Among them, we will just see some view graph about agriculture and soil and land degradation. Prisma is a payload that stays for hyperspectral precursor of an applicative emissions and is composed by a payload include a Prisma-based image spectrometer ranging from the visible to the short wave and integrated with a medium resolution panchromatic camera between, sorry. Okay. And the Prisma main objective, mission objective, have first of all the demonstration and qualification of hyperspectral mission, Italian hyperspectral mission, to acquire worldwide hyperspectral panchromatic imaging worldwide, and also implement a pre-operative mission to support the management and the management of the environmental risk. This is the main issue for us. For this, that supported this research project. At present, the status of Prisma is closing the CDR, and launch is scheduled within the 2018. Just few information about the mission. The coverage is the global coverage is obtained in 29 days. The look time is of 6 days, but it can obtain that can be obtained just by the off-nadir angle of about 21 degrees. The latency is for the Prisma system at present is provide image to the end user in 9 days, including the 6-day maximum relux time due to the cycling of the orbits. The table is a short summary of the characteristic, the main Prisma characteristic. As I told you, is a Prisma as the Prisma diffraction beta, so the spectral interval is changing between the visible and the short wave range from just to 7.5 to close to 12 for the short wave. And the ground sampling distance is about 30 meters for, obviously, for the visible near infrared and the short wave, while for the panchromatic is 5 meters. The signal noise is what we obtained formally from ASI for the last calculation that is quite higher with respect to requirements. But basically, for the output of the research, the 5 research project that was funded by ASI, we noticed that this signal-to-noise ratio is compatible with most of the science applications that we have exploited. Prisma has been designed with a cooling passive system with a working temperature about 185 degrees Kelvin, and the separation between the visible and the shortwave optical paths is obtained by a dichroic beam splitter. You can see a picture of the assembly of the instruments, and on the right side you can see the optical path design for the sensors. Basically, for the audience, that if we want to have more detailed information about the Prisma mission, I want to point out the talk done by my colleague the day after tomorrow in the morning session of the remote sensing application. So over there you can find a precise presentation about this payload. So please refer to them for the technical aspect about this payload. Moving to, obviously, I don't, just for question of brevity, I do not say that the output of the, not included slide, just to say that the output of the Prisma mission is level 1, level 0, 1, and 2, and from level 2, or at least 1, according to the project, they started the environmental products delivery. Among the products that we have analyzed in our project, I want to focus just on agriculture, including the soil properties and the crop parameters retrieval methodologies. We have analyzed the vegetation components, soil components, and crop components. You can see also from the previous presentation, basically the biophysical parameters are the same. So each project have explored the potential of the sensor in retrieving these parameters. We obviously tested the live index, the chlorophyll, the fraction of synthetic active absorbed radiation, and so on. Like for the soil component, we focus on the texture analysis. That means we have explored the Prisma just to retrieve clay, silt, sandy percentage to characterize the soils, and also the carbon organic component percentage. Regarding the crop component, we just moved to, let's say, the level 4 products in which we are trying to assimilate these variables in crop models just to retrieve an information about yield status of the characteristic of this yield. Regarding soil, what we have done, we have experimental farm close to Rome, very close to the Fiumicino airport that we have normally used to take measurements on the ground. Also, this is a very modern farm, so have GIS can provide to us lots of information that normally it's quite difficult to acquire. And you can see on the in the middle there is a field in which the black dots represent where we've sampled the soil, and we went to the lab just to measure the clay sands and the organic content on the lab, so they have used this as true data. We have defined a processing scheme that you can see in the center, in which we have tested the difference between the accuracy we can retrieve by applying the ordinary kriging just on the true data, or use the remote sensing data just to figure out how there can be the accuracy in retrieval of these parameters. So we've done two strategies. One applied to all bands a PLS, so partially square regression analysis, or we decided just to figure out, to visualize which are results by transforming these hyperspectral images in NMF band of principal component analysis, or at least on the PLS latent variables. On these, we applied the ordinarily square regression. At this point, we have two steps. There is no residuals on the image. That means the PLS perfectly map and in this case, the texture of the soil, or we applied a further level of process, that is a linear mixed effect model that takes into account this non-random, the autocorrelation that cannot be detected by PLS. We can see on the right side, we have the retrieval of clay, sands, soil organic matter, performed by this type of analysis. On the right side, you have the standard deviation that we have derived on this data. Regarding the MVG component, we basically develop our application by inverting the presale model, and we have done this starting from the BVNet algorithm that was proposed by Barret in 2007, and we trained this network by using the different variables that you have, the choice of variables we have on the right sides, but basically with respect to the other sensor, we developed a model which transformed the output of the presale models, that is reflectance, but also light, chlorophyll, and other parameters, to a Prisma-like spectra to be used to train the neural network. Obviously, 2/3 were used for the training and 1/3 were used for the validation of the neural network. These are 2 minutes. These are results we apply both for the Prisma, the entire data set, for the vegetation index and for the Prisma component. We can see that the results are obviously different. This was done by using more than 52,000 prosale simulation. As I tell you, this was the next step, just to use these variables within crop models to derive yield estimation, and we have done this in some fields in this farm, and we have measured and estimated in terms of yield tons for hectares. Another aspect that is very important for Mediterranean countries like Italy and Israel is the land degradation. That we focus that the land degradation is clearly not due just to few parameters related just to Earth observation, related to retrieval, can be retrieval by Hyperspectral, so Earth observation, but also by focus on climate and land management. We focus just on two, that is vegetation and soil, but with different procedure with respect to what we have done on agriculture, because agriculture must be more precise. Here is more on mapping. These are two indicators we have among the one we have developed. We have just two indicators, just like samples. The one is we have defined the grand size index in which it identified the areas prone to erosion, highlights the different levels of vulnerability. The index is quite simple, but we have noted that by using, in this case, an Hyperion time series, because we have some data set of 10 years of data set within some part of southern Italy, we apply the index, we notice that there is a differences across time. You can see this graph on the right side, on top on the right side, which gives the difference between this index between 2001 and 2012. They noted that some area highlighted in red correspond to the badlands areas of that specific area. While by using this, the same time series, but approaching the hyperspectral data set for an ecological stability, from an ecological point of view, we have determined the procedure for processing on an unsupervised, clustering and in a supervised way this Hyperion 10 series, just to derive, to visualize if you're able to monitor the ecological stability. We are trying to quantify this by using the landscape meter indicators. We notice in some area, for example, there's an example on the difference in cohesion between the 2003-2012, let's pop up some increment in cohesion in some areas. This correspond, looking at orthophotos, to expansion of artificial wood planted areas. That means that this area increases its stability because of this implantation. Finally, it's all this information, there's a land degradation is a combination of different factors. It's not just by vegetation soil, but we have also climate, social data, and so on. We have decided to implement in an index of vulnerability to land degradation based to the environmental sensitive areas approach of COSMAS in 1999, in which we apply all this information. The one was retrieved by EO data, in this case Prisma-like data, and the other information. We retrieve this IVDL, the Vulnerability Land Degradation Index, and we show on the right side the difference we observed between 2001 and 2012, in which the red areas correspond to the badlands areas in that in this Hyperion footprint. Just concluding remark, if I have some few seconds more. Main conclusion that Prisma is active, it is ongoing. Hopefully, the launch is scheduled to be on 2018. Prisma Signal to Noise is compatible with most of the land and ocean application, but I just refer for land is surely compatible. The project has explored the usefulness of Prisma hyperspectral imagery for the agricultural and land monitor application, specifically for land degraded area. But basically, we say all the environmental application will surely benefit of both energy of the other hyperspectral mission I just referred, not because EnMAP play here on the stage, but surely for EnMAP, but also the ISU and Aspiri in terms of temporal spectral resolution. You have two sensors. If you have two sensors on the space, the repetition time obviously increase, but I would like also to outline the potential that we can have, the benefit we can have for the sentinels in terms of temporal, spatial, and coverage. That's totally different. So there is a very tight link between these two, the hyperspectral and also the sentinels. That's it, and thank you for your attention.
Thank you, Dr. Pignatti. I would like to close this session by thanking all of you being here so late, and of course all of the speakers for their excellent talks, which have demonstrated that spectroscopy from afar is a promising technology not only to find water on Mars or perhaps to pave the road for finding life on the planet, but also, much more importantly, to improve the environment here on Earth, where life has been established millions of years ago for the benefit of all mankind. I thank you all for your attention, and I will close this session. Thank you very much.